Alright, here's chapter 4.2, Gravity and Free Fall. This will be the last chapter before we take our test on one-dimensional motion. Alright, objectives are to find the conditions for free fall, describe and analyze the motion of an object in free fall using the equations for constant acceleration. Here's assessment questions that we'll come back to at the end. A pitcher on a baseball team throws a high lob across home plate. For each part of this event described below is the ball in free fall with an acceleration of 1 gravity. The outfielder is winding up to throw the ball. The ball is in the air rising to the top of its arc. The ball is in the air descending toward the plate. The bat is connecting with the ball. Ball is thrown straight up at 15 meters per second. How long does it take to reach its highest point? What height does it reach, assuming it started at a 0 height? Alright, terms we have acceleration, quadratic equation, and free fall. Our equations here, v, which is our final speed, equals our initial speed plus acceleration times time. And the next one is our final displacement equals our original displacement plus our original velocity times time plus 1/2 acceleration times time squared. An object is in free fall whenever it moves solely, this is the important part, solely under the influence of gravity, regardless of its direction. A ball falling down with negligible air, so going down, gravity's pulling it down. A ball thrown straight up, because gravity is going to slow it down, and a ball launched at any angle as long as there is negligible air resistance. So as it goes like this, gravity is going to be pulling it down the whole time that it's in the air. Near Earth's surface, free-falling objects have a downward acceleration of 9.8 meters per second squared. If an object is dropped from rest, then after 1 second, its velocity is negative 9.8 meters per second. So it's negative 19.6. What would it be after 3 and 4? So then it would be negative 29.4, and then after 10 seconds, it would be 98 meters per second. You see how it goes, and we have a graph here also showing the graph, or the slope of the speed or velocity time graph would be the slope would be the gravity. The free fall equations are identical to the equations of motion with constant acceleration. So we talked about these earlier. The only difference is that you already know the acceleration, because 9.8 meters per second squared is what you're going to use for the acceleration. You already know what the acceleration is going to be. Use this equation for free fall to find your own reaction time, the time to catch a falling ruler. Make a prediction first. Will your reach time be in seconds, tenths of seconds, or hundredths of seconds? Rest your hand on the edge of the table or your desk. Your partner will hold a ruler vertically with 0 centimeters end of your hand. By doing this, you can practice this on your own. You can have somebody at your house, if you have a ruler, and figure out how fast your reaction time is. Your partner will release the ruler, catch it with your thumb and index finger like this. Recall the free fall distance x from the 0 centimeter end of the ruler to where your fingers caught it. So this will end up being your x distance. Now solve this equation for the reaction. There, on page 117 in your book, there's this little formula that you can do for this. What is XO? What is VO? And what is acceleration? Hopefully you know what these are. What was our original distance? What was our original velocity? So XO would be 0, VO would be 0, acceleration would be 9.8. So if an object is dropped from rest, and so on and so forth, for what we just said before, each second with this slope, do falling objects really keep moving faster and faster? The answer to that is yes, because they are accelerating. Meters per second squared shows you acceleration, so they're getting faster and faster every second. Do falling objects really keep moving faster and faster? No, in real life there is air resistance as falling objects speed up the force of air resistance, but most of the time we're going to be talking about problems that don't have air resistance. When the air resistance gets strong enough as the force of gravity, the falling object stops accelerating. This is called terminal velocity. Terminal V, terminal velocity. So that's whenever something going down, the force of gravity going down equals the force of resistance going up from the air resistance. They meet, they cancel each other out, and then you get no more faster movement. Like I said on the previous slide, most objects reach this terminal velocity within a few seconds of being dropped. The terminal velocity is the maximum velocity an object reaches because of air resistance. Human falling has a terminal velocity of about 140 miles per hour. Parachutes will increase air resistance. Opening a parachute changes the terminal velocity from a fast, deadly pace to a low, slow pace. If you look at what happens here, as it's falling, you see the speed versus the time. As the speed is going up, he's falling, he's going faster and faster, and all of a sudden he hits a terminal velocity. He opens up the parachute, and then the speed goes down, and he reaches his new terminal velocity. So this is the first terminal velocity, and this is going to be the second terminal velocity, without parachute, with parachute. So it shows you here at the 28-second mark is where the parachute opened and he slows down. Diving into this a little more, what is happening to the acceleration during each of these line segments? Here, what's happening? He's speeding up, he's in free fall. At this point, he reaches terminal velocity. Then right here is where he opens up the parachute and he gets drag, more air resistance, and then he starts to reduce his velocity until he reaches his other terminal velocity. Alright, here is more words, what I just said to you, explaining what happens. You have zero acceleration because you have terminal velocity. Zero acceleration, terminal velocity. Free fall is not a good approximation for light objects, or an object with large surface areas compared to its weight, like a parachute. Free fall is a very good approximation for solid, dense objects from 10 meters or so. For these situations, air resistance can be ignored. It's not falling so far that air is going to take up and resist it that much. And if you use something solid like a baseball, you're going to get pretty decent accurate readings. For these situations, air resistance can be ignored. The symbol G is often used when the acceleration of an object is only due to gravity. So if you see me write G on a quiz or test or anything like that when I write a formula, I'm saying that the acceleration is what gravity. Define your coordinate system. If you decide up is positive, then down negative 9.8 is going to be gravity. If you decide down is positive, then gravity would be positive 9.8. Most of the time we use, it'll be explained in the test, and I'm going to explain this more in class when we start doing some sample problems with this. Write the equations of motion substituting G and A. Eliminate any terms that are zero. Work out a solution strategy. So we're going to do a lot of this in class. Alright, from what height should you drop a ball if you want it to hit the ground in exactly 1 second? So let's go through what we know. We were asked for what height it needs to be dropped, so we're looking for x, and we're given the time of 1 second, and we know that gravity is negative 9.8 meters per second squared. We can assume the initial velocity is 0. Anytime you drop something, you will start from 0, and you can assume that our initial distance is 0, that it's going to drop. So our formula is our final distance, that's what we're looking for. We said our initial distance, xo is 0, so that will cancel. We said our initial velocity is 0, so that will cancel, leaving us just with x equals 1/2 at squared, where a is going to be gravity. Looks like they canceled stuff out just like I did. So you end up with our final distance equals 1/2 times negative 9.8 meters per second squared times 1 second squared equals negative 4.9. The negative m below the initial position. So we're saying that down was our negative 9.8 meters per second squared. How far does an object have to fall to reach a speed of 10 meters per second? So now we're asking for the different part of this. First we asked for how high it had to be dropped. Now we're going to ask for how far does the object fall to go 10 meters per second. Again, we're looking for x, we're looking for v, a is going to be gravity, we're assuming VO is 0 and XO is 0. So again, we're using x equals XO plus VOT. So this time, and we have another formula here that goes with this. I'm going to show you another formula in class that will help with this. So I'm going to add one more formula to this. That's going to be v squared equals VO squared plus 2AX. And that will help you solve for this little bit. Oops, that's supposed to be squared there. This will actually cut out this step that you don't have to use, but we'll go ahead and do it the way this time. So for this one, you had v equals at, where we solved for t and found out that it took 1.2 seconds, and then you plugged that into this equation now to solve for the negative 5.1 meters. But if we use the v squared equals vo squared plus 2ax, we could have solved it right away because vo we said was 0. We're looking for v squared. We know 2, we know our acceleration, and it asked for x. The ball thrown upward is in a free fall as soon as the person is no longer touching it. If the ball leaves the boy's hand with an upward velocity of 15 meters per second, how fast is it moving 1 second later? So let's take a look at these. What is the sign of VO? Is VO positive or negative? What is the sign of A? Is it positive or negative? Alright, so we're using negative gravity, and we're saying the positive VO is going up. It's going to be positive. Because it's going up, we're saying up is the positive direction and down is negative. So VO is positive and A is negative. So V equals VO plus AT. So VO is 15, A is negative 9.8, T is 1 second. So it'll be going 5.2 meters per second after 1 second. Here's the velocity time graph for a ball thrown up at 15 meters per second. The slope of the velocity of time graph equals the acceleration. So any VT graph, if you look at the slope, it gives you the acceleration. Any slope. This slope right here is the acceleration. And since it's going from a positive 15 meters per second down, we have a negative slope, so we have a negative 9.8 meters per second squared. So remember, slope is rise over run velocity here. Time here. That's how you have your rise over run. When does the ball reach its highest height? How do you know that? Well, where on this chart, let's look on this graph. I have a graph here. Where would it reach its highest point? If I threw this straight up in the air, what is the velocity of the ball at its highest point? This would be the highest point because its velocity stopped at 1.5 seconds because its velocity is 0 for an instant. But it is not 0 for acceleration. The 0 is still negative 9.8 meters per second squared. The velocity stopped, but the acceleration didn't. An object thrown upward. Here is the position time graph for a ball thrown up at 15 meters per second. What is the highest height the ball reaches? So now we have a distance time or position time. So we go up, up, up till this point right here. What is the highest point? So we're going to go across. It's a little over 11, it looks like. How did you know that? It is where it's farthest from the origin. So here's your origin, the farthest point from that would be how high it went for a DT graph, or at 1.5 seconds, like we said back at the other one, where velocity was 0. Alright, now our assessment questions now. A pitcher on a baseball team throws a high lob across home plate. For each part of this event described below, is the ball in free fall with a constant acceleration of 1 gravity? Look at these and let me know. First one, no. The outfielder is winding up to throw the ball. If it's in his hand, it's not in free fall. That's not going to work. The ball is in the air rising to the top of its arc. Yes. Only gravity is affecting it. The ball is in the air descending towards the plate. Yes. Gravity is affecting it. The ball is in contact with the bat. No. Gravity is not the only thing affecting it. A ball is thrown straight up at 15 meters per second. How long does it take to reach its highest point? So we're looking for time. What height? We're looking for x. So how long does it take? We're saying it starts at 15, ends at 0. Gravity is negative 9.8. So looking for this, rearranging, 1.5 seconds. You need to get used to looking at these formulas and figuring out what you have. You said the final velocity was 0. So rearranging this, you got g, or negative VO divided by g. You can never have a negative time, so you got 1.5. Alright, what height does it reach? It started at a 0 height. So we're saying it was in the air 1.5 seconds from our previous problem. It started at 15 meters per second, ended at 0, and acceleration is this. So what we're looking for is the height, x. Okay, so we said xo is 0, initial velocity was 15, it was in the air for 1.5 seconds, we have our 1/2, the acceleration is gravity, and another 1.5, giving us our 11 meters per second. We got to get used to using these. We'll be doing these some of these problems in class.